Okay, this is project 2 by Colin.
And Rain.
And Myra.
Okay, the problem. Two boxes, as you can see below, the blue and red one, are sitting on a level, horizontal, frictionless table. On the left edge of the pit table, the blue box is in contrast with a spring, which is represented by the constant K, has been compressed by a distance of xi. Starting from rest, the blue box begins moving to the right across the frictionless surface until it collides with the red box. The boxes, now stuck together, slide towards the right edge of the table where they encounter a spring identical to the one on the other side of the table. Determine the maximum distance that the second spring compresses. Understand and plan. The known in the problem is that there are two boxes with different masses. The blue box is in constant contact with a spring. The spring with constant K is compressed by a distance. When the box begins moving to the right, it stays in motion until it collides with the red box. After they collide, the boxes are now stuck together, sliding together to the right. They continue to stay in motion until they encounter another spring. The unknown in this problem is the maximum distance the spring at the end compresses. Identify assumptions. We can assume that the surface is frictionless. We can also assume that the spring is an ideal spring that obeys Hooke's law with a force that is linearly proportional to the displacement from equilibrium. We can also assume that the gravitational force is not used throughout this experiment. The collision of the two blocks are entangled as they both move towards the opposite identical spring. Okay, represent the situation physically. As we can see on the right, we have an energy graph compared to the potential energy and kinetic energy compared to time. As we can see, the potential energy starts high with the spring compressed, and then it transfers over to kinetic energy as the boxes move to the right. And as it moves to the right, they get entangled and also then compresses the spring, which then also increases the potential energy. On the bottom, it is similar, as it is basically showing the same thing, but with a different diagram or graph. The spring potential energy is transferred to the first block, which then transfers to the second block and gets entangled and combined, which then transfers to the potential spring energy to the opposite side.
Okay, so calculate. The variables we use is K is the spring constant, M sub B is the mass of the blue block, M sub R is the mass of the red, Xi is the compression of spring 1, VB is the velocity of the blue block, VR is the velocity of the red block, SYS is the velocity of the system, D is the compression of spring 2, which is what we're trying to find. And the equation used, we used the conservation of momentum, the kinetic energy equation, and the potential spring energy equation. For the first part of calculating it, we want to solve for the velocity of the blue block, so V sub B, after it leaves the spring. So as you can see here, we used the potential energy equals kinetic energy, which is the conservation of energy. The potential energy is the potential spring energy, which is why we used 1/2 kxi squared. And then the kinetic energy was 1/2 mv squared. We used the mass of the blue block and the velocity of the blue block. So using algebra, we rearrange the equation for it to equal V sub B. So on the right, you can see all the work on how we got that. The second part of the equation, solving for the equation, is using the momentum conservation to solve for the velocity of the system after the blocks collide. So we will use the value for what we found for V sub B in the last problem and plug it into this equation. So as you can see, we just use algebra to rearrange this equation. V sub r is the velocity of the red block, which is initially at rest, which is why we put it at 0. And after rearranging the equation, you can see what we got down there, and we plugged in the answer we got for VB in the bottom of the equation there. And lastly, for the calculation, we again used the kinetic energy is equal to the potential energy to solve for the distance the spring compresses, which was d. The difference between the first equation and this is that the potential for the second is the potential for the second spring, and the kinetic energy is for the system, not just the first block. So it's both the blocks combined. We again plug in what we found for the last equation, velocity of the system, in order to have the equation in terms of known variables. On the right, you can see all the work that we did to get there. And at the end, all of the values are plugged in, so VB and the system. Okay, and then lastly, we plug in numbers. So we weren't given any numbers in the equation, so these were just made up. The special case that we used was if the red block, the block initially at rest, had a mass of 0, because if it has a mass of 0, the second spring should compress to be equal to the distance the first spring compressed, since they are the same type of spring. So we used 5 kilograms for the mass of block B, 0 for the mass of block R, which was the red block. For K, we used 60 newtons over meters, and we said it compressed at a distance of 0.25 meters, which when solved, we do get this, that the second spring compressed an equal distance to the first spring. So D equaled XI, which was 0.25 meters.
Now we'll be making sense of our answers. So are the units correct? The units for distance is in meters. So if we write out the units for each quantity in our symbolic answer to find the maximum distance that the second spring compresses, we'll end up with meters, which we show on the right. Is the numerical answer reasonable? Yes, when solving for our numerical answer, we use a special case scenario. This was to ensure that the answer we got was correct, since we didn't have values to compare it to. The special case was giving the red block a mass of 0 using this method should have resulted in the compression of the second spring being the same as the compression of the original spring. We know this because of the law of conservation of energy. So when we plugged in numbers, the value we used for XI, the compression for spring 1, needed to be the same as D, which it was. Does our symbolic answer make sense? Yes, our symbolic answer makes sense because we first use the equations of the spring's potential energy equal to the kinetic energy of the blue box, since the blue block has kinetic energy from the compressed spring. Once we found the velocity of the blue box, we then use the conservation of momentum to find the final velocity of the system after the collision. Lastly, we use the equations of the spring's potential energy equal to the kinetic energy of the whole system, which is the 2 boxes, to find the distance of the second compressed spring. How does this relate to class? In the studios, we talked about the spring forces on a frictionless surface in week 6, and where we also talked about the formula of momentum of collisions on week 9. We also talked about kinetic energy on week 7. These all relate to the problem with the spring force formula from week 6. The kinetic energy formula from week 7 and the entanglement information from week 9, which we use in this problem. This all just shows how the class's homework and project tries to combine our previous learning to create a more concrete experience where we could show our comprehension of these subjects.
Thank you.